Okay, so this is the second video of two in the double angle identity angles. Last video we looked at how we established these three double identity angles for sine and cosine. This video we're going to apply it so you can see where we apply work in terms of the trigonometric function. So if we look at this first question here, what we've got here is it's asking us, show that sine x minus cosine 2x plus 1 divided by sine 2x plus cos x equals tan x. So whenever we look at these types of questions, the first thing that I like to think of is, where am I going, what's my final answer look like, and is there any other way that I can show that answer? There is another way that I can show tan x here. I know that tan x is the same as sine x divided by cos x. And that's going to help me out a lot because I can look at this equation here and say, well, I've got some type of fraction here, and because I've got a fraction here, I must have this way of writing to get that tan x. And what that allows me to start doing and thinking is, well, how am I going to start manipulating the top so that for I've only got sine and I've only got cos down the bottom. So, and the way we do that is by using our identification of where we can see double identity angles. So if we look at this first part of the question up here, let's look at the top part. The top part, if we look very, very closely, we can see that at this point here, I've got a double identity angle, okay? Because it's cosine 2 times something. Now, because I want to get top into sine, I want to choose one of these that's going to help me out the most. Now, I could say, well, let's just replace cosine 2x with this. And I'd get my answer, but what happens there is I'm going to have to do a little bit more work, so that way I can actually get it down. So remembering, I want to get sine up the top by itself, and I want to have cosine down the bottom by itself. So if I want sine by itself, I've got a double identity angle that I can replace with cosine 2i just in terms of sine. So I know up here I can now use 1 minus 2 sine squared a. So everything up the top is now with respects to sine. Similarly, down the bottom, I've also got another double identity angle here. However, it's a sine double identity angle. I don't have the luxury of having one or more that's in terms of cos. I've only got one, which is 2 sine a times cos a. So let's now plug both those identities in its expanded form and in its transferred form to see our next step. So we're trying to work out the left-hand side. So let's work it out. So we've got sine x minus, now it's minus all of this. So let's put brackets around it. 1 minus 2 sine x plus 1. All over, we're now replacing sine 2x with 2 sine x cos x plus cos x. Now sometimes it's good to put into the side here, so we can say as cos 2x is equal to 1 minus 2 sine squared x, and as sine 2x is equal to 2 sine x cos x. So what we're doing here is we're explaining ourselves. How did we change these to that? Because of the fact that we've got two identities that we can use to simplify. Okay, let's get to the next step. So the next step here will then be, let's expand any brackets. Sine x minus 1 plus 2 sine squared x plus 1 all over 2 sine x cos x plus cos x. If we look very carefully, we can see here that both these ones can cancel out. Okay? And then we can also see, if we look very, very closely here, that we can start looking at simplifying at the top by factorising out some values. So we could say let's factorise the sign out at the top. So we'd have sine x brackets 1 plus 2 sine x. Remembering that when I take when I factorise by sine x, this effectively drops down to 1. Okay? So remembering that here, if we look at this function here, this is the same as writing 2 lots of sine x all squared. Okay? So therefore, if I'm dividing by 1, so if I'm dividing by sine x by 1, then those just cancel out. And that's essentially what I've done in this step here. So if we look at the bottom, there's nothing to do down the bottom except for doing exactly the same thing. We can factorise cosine out. And hopefully after this step, you will see our sine and cosine appear. Okay? So what we've done in this case here, we've used the double identity angles to simplify it to allow us to reduce our equation from something that looks quite complex to something that is simple. So in this case here, we can look at this and go, well, these two are exactly the same. Even though they're written backwards, they're exactly the same. So therefore, we end up with sine x on cos x. So we can write a little statement over here. So therefore, the left hand side is equal to the right hand side as required. Okay, so this here is an example of how we use the double identity angles and identify it in some trigonometric function to simplify it to get us the result we're looking for. Some key things: think about your end result. What does the end part look like? Is there another way that I can write this? Okay, once you've done that, what do I have to do, okay, to the top for that to work? What do I have to do to the bottom for that to work? Look for any identities, okay? In this case, we're looking at double identity angle identities, and we can see those quite clearly in these. And then we just start looking, especially for the cosine, what type or what transition of cosine double identity angle would work best in this situation. I hope that made sense. Good luck with your questions, and I'll see you next one.